Got it backwards.
So,
Huh?
Also, yesterday. Well, remember there's all these questions.
here we have area A1 and a distance. Didn't leave myself a good place to label it. So I'm going to just say thickness V1 delta T. And this is how much fluid flows past this point in some time interval delta T. Then, over here we have a similar picture. We have A2, and we want a thickness V2 delta T such that the volume of this thing is going to be equal to the volume of this thing, right? So I'm just going to start it out for you. How long do you think that thing's got to be? Longer than this or shorter?
Longer.
Okay, it's got to be longer because it's got less cross-sectional area, right?
Right.
It's got half the cross-sectional area. It's going to have to be 4 times as long. Now, the way I've drawn this, it's got probably 1/10 of the cross-sectional area. It's going to have to be really long, so I'm not going to have this quite to scale, but so the thickness here is V2 delta T, right? Now these have to be equal so that your relationship is let's squeeze it in over here. This. Okay? So V2 equals A1 over A2 times delta T. And this makes sense because from the picture, A1 is
Where's V1 at in
That's
that?
where delta T should be.
time,
I see.
not
Delta
times
T
delta
change.
T times V1. Okay? Again, now, you know that V2 is going to have to be bigger than V1 because if you imagine how much fluid flows past this point, how far it flows, and then how far it has to flow here to flow the same volume, that it's going to have to be faster here. That's pretty easy to grasp. And you want to think about it until you've totally grasped it. Then you look at your ratio and ask yourself, did the ratio I use make sense, or is it an inverse ratio?
I think I did the inverse.
Yeah, well, you did the inverse. Well, you did a straight ratio,
Yeah.
okay? But you always have to ask yourself, is this ratio inverse or is it direct? Is it a ratio with the square or the cube or the square root? Okay? You know, just what is the nature of the ratio? It's not always a simple ratio and it's not always a direct ratio. So, we have this, and now we can check this against intuition. A1 is bigger than A2, so this is greater than 1. So if you multiply that by V1, you find that V2 is greater. And that's where you check it out. Anytime you, and I want you to reason by proportionality, so your instinct to do that was really good. You then have to check out at the end to make sure your ratio makes sense. Simple as that. Okay? Now your book is going to give you a continuity equation, which is just what you get when you divide by delta t here. Okay? And they call that the continuity equation. I call that unnecessary at this point. Because you can use the continuity equation without understanding the continuity equation. But you can understand this, and you can understand this picture, and you can understand this reasoning, so you won't screw up the continuity equation. Now, the continuity equation is important because it gets modified a little bit and applied pretty universally in fluid dynamics, okay? So it's a very important equation, but I don't start with the continuity equation. I don't even give it the name. This is what happens, okay? Then when you see the continuity equation, you say, oh, duh, why do they call that anything? It's just obvious. Yeah,
So what happens along the curve of the bottle?
the curve?
Yeah, where it's not uniform anymore.
Well, if the bottle's changing shape, now within here,
Yeah.
well, at any point in here, well, the pressure is going to, well, we'll see in a minute.
All right.
But the pressure is going to be decreasing. Pressure has to decrease if this thing's going to be going faster than this one. You got to use up some pressure, just like the decrease. You have to have a decreasing pressure here in order to get an increase in kinetic energy. Okay? If P2 actually, something might be wrong there. I'm going to think about that off camera while I have you think about something else.